Saxon's Calculus, Lesson 75, is about U substitution, change of variable, and then proof of the substitution theorem, which of course I'm not going to do. So section A is U substitution, which we already know, and there's only one minor tweaking here. So example 1 says integrate 40x with x squared minus 4 to the 5th power dx. So if we assume that our u is the messy stuff, x squared minus 4, and we always derive that, and we would get 2x dx, then the extra step here is to take this statement and solve for the x dx part. So that would give me dividing by 2, so du over 2 for that part. Now, when I go back, now that I have that, when I go back to the original, I'm testing the u to the 5th. And so what would that have given me? Well, 1/6 u to the 6th. All right, now, if I plug in 1/6, the u was x squared minus 4 to the 6th du, I didn't write that, multiplying with 2x dx. That's not quite, well, I can simplify these together and get 1/3 x squared minus 4 to the 6th x dx. All right, so I have my I'm looking for what I need to fix to adjust it to get back to where it should have been. So the part I had not used is the fact that now we have this extra 1/2 in here. It's affecting both sides of the problem. So it's changing this 1/3 into a 1/6. I realize that put it back. But then it's also affecting the constant, which is technically moved out here. So 1/2 of 40 makes it 20. So what I have here is now the 20 over 6. Now that will reduce to 10/3 with my substituted information to the 6th power. Yes, x squared minus 4 to the 6th power plus the c. Now let me mentally check that, because the 6 will go here, creating part of the 40. Give me the 20. The 2, when I derive it, changes it back to the 40 and provides me the x. And then this stuff to the, so the 6 came down, yes, and then dropping it to the 5th. Yes, that should be correct. It's the extra part is fixing the fraction that is in here. Example 2, find the derivative of 20 cosine of ax dx over square root of b plus sine of ax. So I'm going to assume my u to be b plus sine of ax. So my derivative should be constant b drops off, sine goes to cosine of ax, but I also have to derive the ax, which goes to an a multiplying with that, and then my dx at the end of that, because that was the differential. Then if I solve for the x part, that's going to be stuck here with the cosine of ax dx. and that moved the a to the other side, making it du divided by a. So that's the part that's going to affect the rest of the problem. Now, this was in the bottom. We try to write it in the top. So we've got 20 cosine of ax, and then b plus sine of ax to the negative 1/2, because I brought it up from the bottom. Okay, and that was the u. So we're assuming u to the negative 1/2 here. So that's going to make it u to the 1/2. Okay, so u to the 1/2, and then what did that do? All right, so I added 1, which is where I got the 1/2. But when I added 1, that took me to flipping that, which gives me 2 in front. And then the sine of ax gives me the cosine of ax. And an a. Again, I'm trying to derive every single part. All right, so now the original had, so to fix this part, I need to be dividing everything by a, which is going to give me this 20 over a, with my u to the 1/2, just trying to keep this organized, and then that also has to be over its 1/2, because I never fixed that part. Okay, then when I take a 1/2 and I get rid of it and I flip it up here, that makes it 40 over a. My u gets substituted back in at b plus sine of ax to the 1/2. The 1/2 I already fixed to here, plus my c. Yes. Okay. I hope you're catching. The extra piece here is affecting the constant and the other side to keep everything in balance. All right, then example 3 says integrate 7x square root x minus 1 dx. All right, so the u is going to be x minus 1. The differential will be du with constant drops off. X goes to 1 dx. Then solving for the x, don't have an x. I'm going to treat this as a plain x. So x equals, and I'm going to treat this as a plain u. So the plus 1, u plus 1. Yes. Now, I'm attempting to, oh, I didn't fix this yet. So 7x, x minus 1 to the 1/2. So when I derive it, that goes to 3/2, flipping to 2/3. X minus 1 to the 3/2. Okay. Then my 7 was the constant. And I need to put, just a second, these fractions are messing with my head. Stop and clarify one thing. I said I'm going to treat this as my u and treat this as my x. That's not really what I was doing. I was solving for x here, which is how I was getting the u plus 1. So I know I'm comparing what I have to where I need to be. So I don't have the extra step here where I have a funny du or dx term that I'm fixing for both sides. So in this case, I need this 2 to actually be the 7. So it's going to change over to 14 because the 3 arrived from the exponent part. So if I fix that, if I derived that to test it, I would get back to the 7. So I know that 14/3 with the x minus 1 to the 3/2 plus the c is a part of the answer. Now I've not fixed all of it because I still have this extra x piece in here that's not coming from my original being fixed. So that extra x piece is coming from putting the 7x with the x to the 1/2, which would in essence give me 7x to the 1 plus a half, 3/2. So now if I integrated that, I would get adding 1, so 5/2. So that would give me a 2/5 flipped x to the 3/2. That x is still technically the u. It's still technically the u. So it needs to come as another, I already put the plus c. So let me put plus here with that one. And then we're writing x minus 1 to the 3/2. And it has its 2/5 with the 7 needs to be fixed. The 7 with the 2 is the same fix of 14, but the 5 is being affected by the 3, which makes it need the 15, and that is the whole part of those. It's just so complicated with multiple pieces and the guessing and the testing. My best recommendation on these is honestly to do a guess, get to this point. If this part is helpful, great. Use it as the fixing of both sides as we did in the other 2 examples. If it does not, then you need to make another guess and then test it to see if it's getting you back to the original. The book does it a different way. It's possible that you will prefer that than my trying to guess and solve in my head, and that's perfectly fine as well. Part B is change in variable, and the change in variable method. Okay. So this change in the variable, for example, if you were given a limit that goes from 0 to 2, but your equation was something like x squared plus 1, and then it has its other part 2x to keep things all balanced, dx. When you do your u substitution here and you say that u equals this, you are in essence changing where your boundaries should be. So if you plug in the 0 to u squared plus 1, you get 1 should be the lower limit. When you plug in 2 squared plus 1 is 5. 5 should be the upper limit that you're going to be actually using at the end. So in example 4, it says use the change of variable method to evaluate, and they give it from 0 to 1, and they give us x sine of x, x sine of pi, x squared dx. So we're going to set our u equal to the, pi x squared, the messy part. Then the derivative of that would be 2 pi x dx, not derivative, differential. All right, now to change, then I need to plug in the 0, so that's going to change this one to pi, and when I plug in 1, I get, wait a second, 0. No, I should still get 0. Sorry, that still remained 0. Plugging in 1 gives me pi. So we're going from 0 to pi, not 0 to 1. Okay, now when we integrate, sine goes to cosine pi x squared, and then that adds the extra 2x. So I also have, with this, I failed to write it, the pi, because it was part of the constant. Now, it's not part of my original, so I need to remove the 2 and the pi, which means that I am multiplying by 1 over 2 pi with that to fix the problem. Now I'm ready to plug in the 0 and the pi. Pi being the higher one. And I believe at this point I would do calculator for sure. So I failed here to write my negative, so that should be, because the cosine going to sine should be negative to work correctly backwards. And then this pi over x squared was actually my u. So for right now, leave that as a u, because we're plugging in these values for the u because we'd already made the adjustment for the u. So this mess isn't here, and this is undoing this. So basically you're doing the cosine of pi on the calculator, minusing the cosine of 0 on the calculator, and then multiplying that answer by the negative 2 over pi. And since cosine of pi should go to -1, and you're minusing the cosine of 0 should go to 1, then you have all of that over the -2 pi. That's -2 over the -2, which basically cancels off and just leaves you 1 over pi for the answer. Okay, example 5. Use that change in variable method to evaluate. And originally they give it to us from 0 to pi. There's a constant of 1/5. Oh, no, there's not. Sorry, ignore that for the moment. It's not there. E to the sine of 5x. There we go. And scratched. Okay, so now, dx. Our u is going to be sine of 5x. Our du will be Sine goes to cosine of 5x with the extra 5 from the 5x dx. Okay, so then we plug in our 0 for here. So that's going to give us sine of 0 is 0. Okay, and then plug in the pi, 5 times, and take the sine of that. That's also 0. Okay, so actually it's just one answer then, because I won't have anything to subtract, because you wouldn't want to undo everything. However, since it is the same thing, and e to the x remains e to the x, even plugging in 0 and 0, that's giving me e to the 0 basically minus e to the 0. And then the fixing part was this 5 that was the problem that wasn't here in the original, so it means I need a 1/5 to fix it. Well, then that's basically e to the 0 is 0. 0 minus 0 is 0. 0 times 1/5 is 0. So that actually ended up being a much simpler problem. And then, of course, section C we're not looking at.